Okay, exam preparation for the AP Calculus exam, part 2 here. And I did example 1 in a different video because that was a calculator question. So that one is complete. And I want to move on to example 2. And this one says no calculator allowed for this problem. So put the calculator aside. And these questions are very interesting. Let me just read what they've given here. The figure above shows the graph of f prime, the derivative of a twice differentiable function f. So the detail of it saying the derivative of a twice differentiable function f just means, yes, you'll be able to take the derivative, so you don't have to worry about that. This is on the closed interval 0 to 8. I can see that on the graph. It goes from 0 and ends at 8. And the graph of f prime has horizontal tangents at x equals 1, 3, and 5. I can sort of see that in the graph, but they're just verifying that at those particular points you do get horizontal tangents. And the areas of the regions between the f prime and the x-axis are labeled in the figure. I can see them there. The area is 2 in that first section, and then 6 in the second, and then 3. Well, is it -3? Well, it's area of 3 below, so we'll have to think about that. And then area of 7 on that last section. And the function of f is defined for all real numbers and satisfies f at 8 equals 4. And I'm going to stop there because that's the first really interesting detail. Well, I mean, there's tons of really interesting details, but I'm just going to highlight that because it comes up a little later when least expected. So I'll just leave that as a random detail right now. Okay, why I said these questions are interesting is because they don't take much work, but the work is really, really difficult to follow. You have to have your own way. You have to come to grips with your own way of understanding what this graph is telling you here. So let's look at the first question. It says, find all the answers for x on the open interval from 0 to 8, so anywhere from 0 to 8, where the function has a local minimum. Justify your answer. Okay, to have a local minimum, let me just write a little sentence here. For local minimum, we need the derivative to go from negative to positive. That's what when we have a local minimum, that's what we're talking about, is we've seen the derivative go from negative to positive. Now, don't look at the graph that they've given for a second. Just picture this in your mind. Normally, when we have the graph of a regular function, not like this time where we've got the graph of the derivative. Normally, when we look at a function, we'd have positive derivatives when the function was going up and negative derivatives when the function was going down. I don't even want to draw that to distract you from what this picture is. This picture is a picture of the derivative. So what I'm going to do is get out my green highlighter and highlight where this graph is positive. It's positive in that section, and in that section, and in that section. I'm just going to stop a little short there because I don't want it to highlight the 0 there. I overdid it there. I didn't want to highlight the 0 here. I want to sort of make it clear that I'm not highlighting the 0. Those are the sections of the graph where this graph is positive. So those are the sections of the graph where the derivative is positive. Okay, that's hard to follow along when you've been doing so much work with regular graphs and derivative meant going up or going down. This is positive values of the derivative. And so I'm going to also highlight in red where this derivative is, where this function is negative, where this graph is negative, and that's the values where this derivative is negative because this is a derivative graph. Well, after all that thinking, all we've got to do is find the value where it switches from negative to positive, and that's right there. At x equals 6, the graph goes from negative to positive, and now I'm going to go back and add a word here. That is, f prime goes from negative to positive. Therefore, there is a local minimum at x equals 6. Boy, very little work to be done there, but very difficult thinking that has to happen. Next, it says determine the absolute minimum value. Now, when it says absolute minimum value, we got to think all the way back to regular calculus and say, okay, when do we get a absolute minimum? And there's these candidates, these nominees to be the absolute minimum. And x equals 6 is one of them. It's a local minimum. So x equals 6 is a candidate. But the other two spots we've got to check are 0 and 8. Now, I'm going to do them in reverse order. I know the solution page that's attached to this does them, it does 0, then 6, then 8. I'm going to do them in the other order because I think it's a little easier to see what has to happen. First, we need to find out what is the function value at the end point. I'm going to do the right end point first, at f at 8 equals, and that was the little detail they gave me at the start. They actually told me the value of the function at f at 8, so that's interesting that they gave me that little detail. Next, I'm going to go after the function value at x equals 0. Me personally, I think it's the next easiest one to see. Now, to get the function value at 0 is very difficult because this graph doesn't give an easy way to get that function value. Because you say, well, I can just look where x equals 0 and get the value right there. Isn't that it right there? And the answer is no. That's the value of the derivative right there, not the value of the function. So here's a weird little procedure I'm going to do to find that value at f at 0. What I'm going to say is, to get the function value at 0, I'm going to start with the function value at 8, and then I'm going to add on to that the integral, and I'm going to go this way with the integral and add on all those areas. That is, I want to start with a function value of 8, and then add on all these net changes that you get from the accumulation of the derivative, all those little Riemann sums, if you will, all the way back here. So then what I want is the integral from 8 all the way back to 0 of f prime at x. Add up all those little pieces that go backwards. Well, that's very strange because we didn't really do integrals 8 to 0 like that or think that way. So what do I got to do to handle this thing? Well, I'm going to go f at 8 minus integral from 0 to 8 of f prime at x dx. And that little move gives you an alternate way to think of this. If my earlier explanation sort of messed you up, is just to say, well, to find out what the function value is at 0, take the function value at 8, and then subtract off all the areas that have been added onto there so that I can sort of rewind the clock back here and find out what happened at, or where this function was at 0 by subtracting off all the little things that happened there. If you want, then if you just look at that equation, you see that f at 8 is, how you get f at 8 is you go f at 0 plus the integral from 0 to 8 of f prime at x dx. Giving you a third way to think about this is to start and go, well, I don't know how to find f at 0, but I know f at 8 comes from going f at 0 plus the integral from 0 to 8 of f prime, and then you can rearrange to find f at 0. Okay, so, well, lots going on there. And then, well, if you've got that, then it's just about areas there. So then f at 0 is f at 8, which we know is 4. And then I got to subtract all those areas that I've got there. So, let's see. What's the sum area there? 2, 8, 15 minus the 3 is 12. That's the total areas from 0 to 8. So I'm actually subtracting off all those areas. And so f at 0 is -8. Boy, that's rough. But hey, here's good news. I'm going to do all that thinking again because I got to now find f at, what was the third candidate? 0, 8, oh, and 6 from part A, right? So f at 6. So again, I'm going to do all three ways of thinking about this at once. I'm going to say, okay, if I wanted to find f at 6, what I could do is take f at 8 and add on to that the integral from 8 back to 6 of f prime at x dx. So I could just go backwards and add those in reverse. And if that doesn't make sense to you, maybe this one will. You could start here and say, well, to get f at 6, I'm going to take f at 8, and I'm going to subtract all these little sums, 6 to 8 of f prime at x dx. And then if that way doesn't help you either, maybe what you'd want to start off with was, well, I know that f at 8 is equal to f at 6, plus the integral from 6 to 8 of f primes, and then you could rearrange from there. So 3 different ways to come up with that equation. And so here f at 6 will be f at 8 minus, okay, I just want the area from 6 to 8 of f prime. So 6 to 8, I think I see area 7 there. So f at 6 is f at 8, which is 4 minus 7. I get negative 3 when I put all those things together. And it says determine the absolute minimum value. Therefore, the absolute min, I've got these 3 candidates. The absolute min is, what were my 3 answers? I got negative 8, negative 3, and 4. So the absolute min value is negative 8. Oh, tough question. That is a doozy, and you're going to have to work through it and find your own way of getting from beginning to end there, because those are tough. Next, on what open intervals contain 0 to 8 is the graph both concave down and increasing? Explain your reasoning. Well, I'm going to go back to my original graph and get out my eraser here, because I really want to clean up everything I wrote on there and really start my thinking again to handle this question. So I need 2 things to happen. I need the graph to be increasing and concave down. Okay, just leave the concave down alone for a second, and let's just go after increasing, because that's not too bad. I'm going to go back to what it takes for a function to be increasing. For a function to be increasing, I need its derivative to be greater than 0. So where is the derivative greater than 0? In here. I'm going to just stop short there. In there. And in there, okay? So all of those spots, the graph will be increasing. Now, the next thing I want is, when will it be concave down? To be concave down, okay, it's going to take a little thought here. I need f double prime to be less than 0 will give my concave down. I need the double derivative to be less than 0. So if I want the double derivative to be less than 0, then I need f prime to be decreasing. That is, then if I take the double derivative, I'd get negative. So what I need is the derivative of the graph I see here to be negative. That is, the derivative of the derivative. So the double derivative. So I need that to be negative. So then I'm going to do some extra little shading here. I'm going to go with like blue. And so here is where it's, oops, that wasn't the highlighter that I was after there. Highlight and not in green, sort of in a bluish there, and say, okay, in this section there, it's decreasing. In this section there, it's decreasing. So I actually end up with 2 intervals that are decreasing, because the function that are increasing because they are both have positive values of the derivative, but also we need these derivatives of this function of the graph there to be negative. So that would give the double derivative to be less than 0, which is concave down. Wow, lots of stuff going on there. So when, what 2 sections here? It was 0 less than x less than 1, and 3 less than x less than 4, f prime is greater than 0, which means it's increasing. Also, when 0 less than x, oops, and 3 less than x less than 4, f double prime, or if you want, f prime prime is less than 0, meaning concave down. I think maybe in the solutions they use the wrong word there. They say, oh no, they do say f prime is decreasing. So they just said it a different way in the solutions there. Wow. B and C. A is not bad. A is not a bad question, but B and C really ask you to know your stuff, to really be able to tear these things apart. And the good news is the only good news is these type of graphs are often shaped the same way. It's just up and down, positive, negative, and you just have to get used to what each piece is telling you and all of that. The last one I'll call the easy question, even though algebraically it's really difficult. It says the function g is defined by g at x equals f at x cubed if f at 3 is negative 5/2. Find the slope of the line tangent to the graph of g at x equals 3. So I've got g at x equal to f at x cubed. I want to find the derivative of this. So g prime at x is 3 f at x squared. Little chain rule times the derivative of f prime inside. There's the derivative of g. Pretty straightforward. Application of the chain rule. Bring down the 3, reduce it by 1, and then find the derivative of the inside. So really weird looking, but not particularly difficult. And then now I want g prime at 3. So what I'm after is 3 times f at 3 squared times f prime at 3. And what's weird about these questions is you sort of have to have faith that when you get to this last step that the information that they're asking for is all going to be there for you. And here it is, like f at 3 is negative 5/2 squared. And then f prime at 3. F prime at 3. Ooh, I need that from somewhere else. F prime at 3. I got to go back up to the graph here. F prime at 3. There it is right there. The value of f prime at 3 is 4. Wow. Make your reach back and get that needed information there of 4. Wow, that was tricky. And so then when I multiply that stuff all out, what do I get? G prime at 3 is 25 over 4. The 4's cancel. 3 times 5. Or 3 times 25 is 75. Wow, that question has some torque to it. Yeah, those really need some work. So you're really going to have to go back and look those over and try some different versions of those to get ready for that type of question. Okay, look that over. Don't get too intimidated by it because it really can be handled. And once you have the weapons available, and then I think most of the weapons are shown here in this example, most of the other examples use those exact same tools and weapons again and again and again. So they are fairly repetitive in that way. Okay, and so then there's some assigned work. Questions 1 and 2 are given in the assigned work, so you can try those on your own. They're a lot like the ones we just did. And then check out the solutions for those. Okay, have a great day.